I'm here to talk about biomass, and biomass from the new-ish satellite LiDAR missions, so GEDI and ICESat-2. And as Fabian said in the opening session before us, when we were in Maryland together, it was like a few months before GEDI launched, right? And I think it was maybe right after ICESat-2 had launched. I'm trying to remember. I think it was like a month after, right? Yeah, so it was like super exciting time for satellite LiDAR. And now here we are. I don't know how it happened, but it's like almost been 4 years. What? And a lot has happened during that time, obviously, with the pandemic. And we've been very busy making products and doing science. And it's a great pleasure to share some of that with you today. I'm representing the GEDI science team as a whole. In particular, shout outs to people who have given slides for this presentation. The PI of GEDI, Ralph Dubaya, John, Amy Neuenschwander's here, and she'll be presenting on ICESat-2 more tomorrow. But also I'm presenting on our global biomass harmonization activity, and many of the participants are here at the conference, and we'll talk more about that. And without further ado, let's jump into it. Okay, so I'm going to start with GEDI, a little refresher on where we're at with the mission and what the biomass products are looking like. And then we're going to add a hat. We're going to add ICESat-2 for the Boreal, where GEDI doesn't sample. And we're going to add them up. And so this is going to be like a mini drum roll moment, because this is the first time that we're going to be reporting on that global total biomass from these two missions combined. So they're both, well, the ICESat-2 one is a bit provisional, so it'll be more like a drum roll and a band practice rather than on a big stage. But this is a very nice, receptive community. So if the numbers jump around a little bit in the actual papers, no one's going to yell at us. Okay, so that'll be like the big, ooh, that's how much carbon, cool. And then we're going to talk about other biomass products, because these are, of course, just two of a suite of new biomass products, and they don't all match. So we're going to talk about resolving differences, where I see at least some areas that we really need to improve in biomass mapping in general. And then I'm going to share some of the kind of cool new research results from GEDI, both from my own work and others on the team. And I'm going to end with talking about a global protected area analysis that we've been working on in my group. That it's kind of like my passion project on GEDI. Everyone's got kind of like a side gig. Mine's, I think protected areas are cool. Okay, so to remind ourselves how much carbon we're kind of expecting to see in these global products, here's a figure from the Global Carbon Project. And this is an estimate of 450 gigatons of carbon in vegetation. That's above and below ground. I think it's woody and non-woody. And this is a rough estimate. In the models, in the data, what we're seeing is that forests are still our friends, right? We're still seeing more carbon sequestration into forests than we're seeing emitted from forests due to deforestation, degradation, etc. We're really hoping that this continues into the future, that all the droughts and the fires are not going to flip it and make it a source instead of having global forests be a global sink. But understanding and mapping where vegetation carbon is richest, is changing fastest. This is really important for improving global models, for informing policy decisions, etc., which has arguably never really been more important than now, right? So we heard earlier this week that the world has indeed made this lofty commitment to end deforestation by 2030, which is like, yeah, amazing, let's do it. It was endorsed by 141 countries, including Brazil, including, you know, countries that we'll see how that goes. But it covers 90% of global forests. So if we can do this, what an achievement, right? This is not the first such pledge. But I think it's really heartening to see the commitments of financial support to specific things like indigenous management of forests, like conservation of the Congo Basin, like billions of dollars of commitment. So hopefully we can actually see deforestation slow down and halt by 2030. And I think this community is going to play a really important role in tracking this, in holding countries accountable, in providing the information and the data to show where we're doing well, where we still need to improve. And I think that the carbon picture that we're providing with these new 3D structure data sets, like from GEDI and ICESat-2, will really help to improve this information. So here's an animation from Matt Hansen's group. So this is like the Glad Alert style group. And this is an area in Brazil from the Landsat record from 85 through till recently. And you can see in this black polygon, this is an indigenous territory, it's a protected area, and you can see forest loss, in this case it is deforestation, just encroaching on that area over time. It's quite a staggering animation, but we've seen many other examples like this week, right? So we can see this forest loss. And then, unfortunately, you even start to see that forest loss within this protected area as well. So we've been tracking this, right? As a community, we've got lots of different products, but how much carbon is being lost when we see this kind of forest loss? Yeah, we don't actually know. We don't have a good estimate of that because we didn't have GEDI 20 years ago. So we don't know how much carbon was there to begin with. We see the loss, but in the future, we will have these biomass maps and we will be able to quantify the carbon emissions associated with this type of activity. Okay, so how much global biomass is there? And this is, the whole presentation is above ground biomass because like GEDI doesn't see below ground, you know, so we're sticking to above ground and we can talk about that later. But how much biomass is there above ground? Here's a couple of estimates from the literature. From a stratify and multiply approach from Rush and Gibbs. This is using like a IPCC tier 1 type approach. The estimate is 690 petagrams of above ground biomass. Okay, and so this is if like a country doesn't have an NFI, they often will use this type of approach. This is the forest area times the mean biomass per different types of forest, and then you add it all up. All right, so that's one type of approach. And obviously, as a remote sensing scientist, I'm like, we can do a lot better with remote sensing because we're actually spatially mapping the distribution. So from a Spawn et al. Paper from 2020, and both of these estimates are representative of 2010 conditions. We have an estimate of 574 petagrams of above ground biomass. Okay, so this is largely based on remote sensing. The backbone of that paper and product is the Global Biomass product from Maurizio Santoro's group. And so I'm calling this kind of like the reference remote sensing estimate. Of course, GEDI is this first satellite LiDAR that was designed to study forests in 3D, and we expect this will be bringing more accuracy to these estimates, especially the remote sensing based estimates, and improve these budgets. All right, so let's talk about GEDI. A few months after ForestSat, last time GEDI launched from Florida, we all went down there. There was no pandemic stress around travel. No one would ever even know what a mask really was, right? Oh, those were the days. So here's the group at, or part of the GEDI team at least, at the launch, and it went up on a SpaceX Dragon capsule to the International Space Station. It was very exciting, and I'll show you a little launch video right at the end of this talk. All right, so for those of you, actually, I'm going to pause because I don't know this. Let's do a little interaction. Could I see a show of hands for who of you have used GEDI data? Okay. And then just for reference, who's used ICESat-2 data? Okay. So GEDI's winning in this community, Amy, I'm so sorry. I wanted to take pictures, but I was too lazy. Okay, so no, that's good. So a lot of you are familiar with GEDI, but not everybody, yeah? So we'll go through kind of like what GEDI is. It's on the International Space Station, as I said, and GEDI has 3 lasers in about a refrigerator-sized box. One of those lasers is split into 2 beams that are each about half the power of the full power beams. So we have coverage laser beams, 2 of those, and 2 full power laser beams. So 4 beams coming down. They're optically dithered back and forth, making 8 ground tracks. So as the ISS goes over, you have these 8 lines of GEDI samples under it, and each individual laser beam illuminates about a 25-meter diameter circle, so kind of washes the forest. You get the first photons back from the top of the canopy, the last photons back from the ground. This orange squiggle is our GEDI waveform, and that's the sort of core observable. And from that, we derive ground elevation, even under dense forests, maximum canopy height, mean canopy height, foliage height diversity, canopy cover, plant area index, and above ground biomass, which I'll mostly focus on. So as you probably all know, it's not a wall-to-wall mapper. So GEDI is a sample mission. It's just set up so nicely for data fusion, except for a little geolocation and uncertainty, which those of you who have played with GEDI data are probably very familiar with. But this is the general spatial distribution for a pass. Yeah, so about 600 meters between shots and 60 meters along a given track. All right, so here's some eye candy for the products that are coming out. So as a sampling mission, the gridded products from GEDI are at a 1 kilometer spatial resolution. So they're pretty coarse, and they take all of, in a 1 kilometer cell, they take all of the GEDI shots and they average them. Yeah, for biomass, it's like a fancy statistical average, and for most of the products, it's kind of more of a normal average. So here's topography after 2.75 years of science data. It's beautiful, right? Here's global canopy height. You see those heights popping up in places like the Pacific Northwest, the Amazon and Congo basins, Indonesia, etc. And then the gridded biomass. So this is kind of the end of the line of the products. And this is the first version of it, but it's going to be getting better and better through time, and I'll talk about that. So this has been really one of like the big missing data gaps, we think, in the remote sensing world. And I'm not going to get super into the details of the algorithms for biomass, but I did want to reflect on how these are largely community-based. And many, many, many people who are at this conference and in the ForestSat community and then in the Silva Laser community have really contributed meaningfully to our biomass algorithms. So what we do for GEDI is we essentially beg data off of people. So we take plot data that somebody's collected somewhere where you can estimate biomass, and airborne LiDAR data that was collected at the same place at the same time. We make the airborne LiDAR data look like GEDI through a waveform simulator that was led by Steve Hancock, and then we process it using the same algorithms we would use for on-orbit data. And we build like the simplest prediction models. Right? So this is like a scatter plot. It's just predicting field biomass as an OLS model as a function of relative height metrics from GEDI. So super simple. And to get here, we've collated a database from community contributed data. So the community is such a big part of this. If you're thinking, hey, Laura never talked to me about this, my data's not in there, come talk to me, because this is a living database and the models are going to be refit through time and improved, especially in places where we have big geographic data gaps. So if you're looking at this map and let's say you have a bunch of data in India, that would be a really exciting thing. So come talk to us, yeah, because we only know how good this product is in places we have data where we can do some cross-validation. In Central Asia, we're quite data sparse. Okay. Moving forward. So if you want more details on the L4A, so that's the footprint level biomass, that's where we predict biomass per individual shot, and then we aggregate those for the gridded product. That's in this RSE paper. And as a fun little anecdote, we pretty much broke RSE's submission software when we were trying to submit a paper with this many authors. It was, there are over 100 authors. These are all of these wonderful data contributors as well, providing intellectual and data inputs to this, this paper. And if you want your name on the next massive monster paper, come collaborate with us and bring some data. So just to quickly reflect on the fact that these are indeed growing products, they're going to be changing as we fill data gaps, as we get new data in, we refit the models, we reproduce the products. So in theory, GEDI's biomass products are going to get better and better through time. So on this map here, every little black circle, that's the stuff that's in the current biomass product. So if you've downloaded it, that's the training data, yeah? Everything in turquoise is stuff we are working on putting into the next version that we're fitting in the next few months. And so there's still time to get your data in there for the next version if we kind of rush. Everything in the boreal, I'll talk about that. That's for our ICESat-2 complementary biomass product. If you do have data, you'll probably be talking a lot to this extremely lovely and patient individual, David Miner, and the co-leads of this are myself, my lovely husband, John Armston, and Jim Kellner, who's also great. Okay, so. All right, so then where does ICESat-2 come into this, right? So GEDI, beautiful, wonderful, tropics are covered, temperate forests are covered. They're missing the boreal forest, or the vast majority of the boreal forest, right? Because the International Space Station doesn't go over the poles. So the astronauts are never like looking straight down at the North Pole, yeah? Okay, so we're very data rich in the LiDAR community. We have ICESat-2 to fill this gap. So here we have the wonderful ICESat-2 mission. And again, please do go to Amy's talk for more information on ICESat-2 vegetation products at large and for this particular product. So we're calling, I like to call this like Jedi's cap or Jedi's hat, but it's we're filling in the boreal, yeah? Okay. So this is like partially using very similar approaches to how we did biomass estimation with GEDI, and then partially going a totally different route for high spatial resolution wall-to-wall mapping. So we'll talk about this a little bit. I wanted to quickly plug that this, like many new and future NASA products, is an open science product, which means you can look at all the code. So if you're looking at the product and you're like, this makes no sense in my study area, like jump on into the code, explore it, and tell us why, and maybe we can collaborate to improve it. Okay, so I won't get into the details of the workflow. I just wanted to highlight we've got a big and wonderful team working on this product. We've got a pretty final provisional product, but we're doing one big rerun for the final one that we're hoping will be released in the next few months. So this is the part that's very similar to GEDI. We essentially, we made like a higher spatial resolution version of ICESat-2 at 30 meters instead of 100 meters. So that was part of this project, and Amy can talk more about that, I think, in her talk. And then we fit very similar flavors of biomass models to what we did for GEDI. So we have simulated ICESat-2 over field plots in the boreal instead of simulated GEDI. Simulator still from Steve Hancock, but change the flavor of what we're simulating. And then we predict biomass as a function of ICESat-2 relative height metrics instead of GEDI relative height metrics, and they're at 30 meters. 30 meters for ICESat-2, why? Why did we go to higher spatial resolution? Partially because we wanted to do Landsat fusion, so fusion at a 30-meter scale for wall-to-wall mapping. A lot of boreal data users were saying this is the scale that we want the products at. And then also the field plots, like in the boreal, there aren't a lot of like 1/4 hectare, 1 hectare field plots. They tend to be smaller field plots, approximately 30 meters in size. So because of those two things, this is the scale we went to. Okay, so it's a bit messy. This is if you took all of the training data across the whole boreal and poured it into one model. In reality, we separate the models out geographically and by plant functional type, like we do for GEDI. But I just wanted to give you kind of a flavor. It's another simple OLS model. So we take these models and we apply them to on-orbit 30-meter ICESat-2 data. And then here's where we depart from the GEDI approach. We wanted to do this wall-to-wall mapping, and so there were several talks in the GEDI session yesterday about GEDI fusion with something, with Landsat, with Sentinel-1, Sentinel-2, and it's such a natural thing to do because these LiDARs are sample missions, yeah? So we did the same thing. We used HLS, so the Harmonized Landsat Sentinel product, kind of growing season composite for the greenest pixel. That's the example over North America, as well as the Copernicus DEM. So those were our mapped covariates. And we did something similar to what we've seen in the literature from other papers. Sean Healy's group's doing stuff like this. Peter Potapov is doing stuff like this. We do, for every tile, we take ICESat-2 training data and make a local random forest model. Okay, and then we do like this brute force massive refitting and iteration to get our per pixel uncertainties. But I don't have to get too into the details on that today. Okay, so then how, like this is everyone's natural question when we're taking GEDI and then we're adding ICESat-2. And they're like, okay, is there like any sort of clear bias between those products? Do you do intercomparison? It's a little tricky because of course we don't have GEDI over most of the boreal, so we can't really do an intercomparison. But we did do a comparison between 50 and 52 degrees latitude. So like where we do have the overlap, we pull ICESat-2 a little further south, and 52 is kind of where GEDI stops. And so this is some work from Veronica Leitold in my group, and we see that in the lower biomass parts of this strip, they match super well. So ICESat-2 GEDI, wow, we didn't actually see a bias. As you get to a slightly higher biomass, GEDI is predicting higher than ICESat-2. So we're still digging into that. We're like, is it that ICESat-2 maybe in those denser forests is missing the ground, or maybe shrinking the tree height? Is this an HLS saturation issue? So we're still digging into this, but we're not too worried about it because most of the areas where we see the discrepancies are actually not in the boreal forest. So they're further south to the boreal. So in the lower actual boreal parts of the overlap, it's pretty much bang on, which is awesome. Okay, so that's like all of this overwhelming information about products. And you're all probably thinking, cool, like let's get to the drum roll. How much biomass is there? Okay, so we're gonna do it. So we're gonna start with the ICESat-2 boreal product. If you add up all of those 30 meter pixels, you get 92 petagrams of carbon, almost 93 petagrams of carbon, with a super duper small uncertainty because we are adding up so many pixels, assuming you don't have bias or systematic error in those OLS models. Your uncertainty when you map every single pixel is super small. I won't get super into detail on the uncertainty piece, but this is what we have. Okay, so we've got almost 93 petagrams of biomass. Now this is about 10 to 15 petagrams more than has been estimated in boreal forests from 2010 products. So from Chris Nye's group, from Maurizio Santoro's papers, they all showed, somewhere between 75, 80 petagrams of biomass in the boreal. So it's like, all right, what's going on? Has there been this massive growth spurt over the last decade? No, because these are like pretty slow growing forests. So we're speculating, but I think what's happening here is that because we're mapping at higher spatial resolution, we're able to see pockets of boreal forest that were kind of invisible to the coarser products. So it's speculative, but I think that that's why we're seeing higher biomass here than past products. So that's cool. That's cool. Okay. Then if you take ICESat-2 all the way down to 51.6. So this is where we do the cutoff between GEDI and north of GEDI. We get 127.7 petagrams of biomass, which doesn't really have an ecological meaning because there's nothing special about that latitude. It's just where GEDI stops. Okay, so then we add in the GEDI biomass totals. And this is from Ralph Dubois. So this is Ralph, if he wishes he was here. And this is a paper that just came out, I think like a week and a half ago, John. When was it officially out? Sorry. Yeah, last week. Okay. Yeah, it's been a preprint for a while, but if you haven't seen this paper and you're a GEDI enthusiast, go check it out. It's an incredible amount of work was put into this paper. And it's talking about the L4B product and GEDI biomass totals, but really interestingly and importantly, it's talking a lot about the approach to uncertainties that GEDI has, which includes like spatial sampling error, which includes like autocorrelation of shots along a track. It's quite a statistically robust and interesting approach to uncertainties. And so where we have, if you add up all the GEDI biomass over, let's say, Brazil, which is the country that has the most biomass in the world, then you also have an associated statistically robust uncertainty, which is really critical and I think is going to become more and more prevalent in biomass mapping, which will help with transparency and hopefully uptake for policy. Okay, so if we take all of the countries that GEDI fully samples, which are shown in Ralph's ERL paper here, all the biomass in all those countries, again, you can see like unexpectedly Brazil pops out as the highest. You've got a lot of biomass in China, in Indonesia, in the US, in the DRC, etc. Add all that up and it adds to 480 petagrams. And then you add the, John Crank, the numbers on this, you add the southern part of the other countries between like Canada, Russia, etc., up until 51.6 degrees. And that gives you a total from the GEDI domain of 506 petagrams of biomass. Okay, so basic math, we add these together and we see that for GEDI and ICESat-2, the total estimated biomass is 633 petagrams. Now recall from the remote sensing product paper in 2010 from Spawn et al., this was 574 petagrams, so GEDI is a bit higher than that, but still appreciably lower than that stratify and multiply approach from the tier 1 paper. Okay, so like Yay, we're done. That was very exciting. What a cool number. Um, so yeah, so it's a bit more than those past products. We will see these are going to continue to refine the ICESat-2 numbers in particular. Those are based on a provisional product we're about to regenerate. So these numbers may change. Don't go and like write a paper just based on that. But in the next couple months, we'll have the Boreal paper come out. Okay, so this is exciting, but of course, this is not the only solution to biomass mapping. There are many other products out there, and I think with all of the exciting new sensors on the horizon, we're going to be flooded with more and more exciting biomass products at different spatial resolutions that are focused on different kind of ecosystems. And we need to kind of make sense of all of those. Otherwise, not only are we going to be really confused as a community, but data users, particularly non-technical data users, are going to be like, the remote sensing community does not know how much biomass there is. They're giving us this crazy big range. All the products don't match. We're not going to use any of it. So we want to avoid that. So we've launched a CEOS initiative, I think almost 2 years ago now, which is crazy. And this is the biomass product harmonization activity, where a bunch of the big kind of biomass mapping groups are getting together, and we're trying to do the work of making sense of discrepancies between our products. Because if we can't figure it out, how are users ever going to? Yeah. All right. So actually, I'll quickly just say, so right now we only have 5 products that we're looking at. We're looking at GEDI. Sasan Sachi's group at JPL has a provisional 2020 product that's like a LiDAR saw fusion product, and CCI Biomass, which has a whole suite of products. Their latest provisional product is also for 2020, which I think will be released early next year, I believe. Then we also have the ICESat-2 Boreal product, and NCEO from the UK has an Africa-wide product. So if you're working on an at least continental scale biomass product, and you're like, I want to also do this with you guys and understand the strengths and weaknesses of my product, totally come join us. The doors are always open. Okay, so oops. Sorry, the website got mucked up there, but you'll see it again in a second. So one of the things we worked on is a dashboard that's both something we use to just visually look at products and compare them, but also that's public facing. So we are trying to just advertise these products in an accessible way. And I'll show you kind of what that looks like. Maybe. Nope. Hold on. I've got to press play on. Yes, okay, that's working. Great. Yeah, so you can go to this website today. It's totally live, and you can see the 5 different biomass products that I talked about. You can click on one of them, in this case, GEDI, and you'll see the associated uncertainty product, as well as the CalVal map, at least the publicly available CalVal data. And you can read up on all the different products. We also, very importantly, are partnering with several countries, because for us to understand the strengths and weaknesses of the products, we really need good reference data. Often that comes from NFIs and local knowledge. So you can read about our kind of official pilot countries here. We also have several other countries that we've started to work with in the last 6 months. So you can just go into your area of interest where you kind of understand the biomass. Let's say this is an example for Peru. It's all cloud-based, so it takes a second for this to load. This is all like in real time. So then in Peru, it'll show you automatically all of the biomass products that are available for that region. You can click them on and off, look at them compared to base layers, etc. So there's the CCI biomass product, again, provisional for 2020, the NASA JPL product, and you can see right away there are some pretty serious discrepancies here, right? So these product teams are now talking to each other and trying to figure out why. And then there's the much coarser GEDI product, which of course has these spatial gaps that are a bit of a shame, but data fusion's a dream. And you can start learning about these products. Okay. So I also wanted to pause and make kind of an important note about a trend that we're seeing both in this community, but kind of NASA, ESA, the space agencies across the board, toward open science. So this harmonization activity was all made on an open science platform called the Multi-Mission Algorithm and Analysis Platform. It's not my favorite name because it's pronounced MAP. So if you're like, I'm making a biomass map on the map with like biomass data from ICESat. It gets really confusing, but this is the map, and it's an amazing tool, potentially despite the name. So this is a bilateral tool that was developed between NASA and ESA in reflection that we need to be working more and more together as a community. So we need to be sharing algorithms, we need to be sharing data, we need to be talking to each other. So the map was created for the biomass community primarily in recognition that we have GEDI right now, we have NASA ISRO's NISAR being launched in early 2024, L-band SAR every 12 days, massive data volumes. We have ESA's Biomass mission being launched next year, P-band SAR. And so to be able to do data fusion in an open science, super transparent way is going to be increasingly important. So this is one tool that NASA has built for this. But I think that this is going to be a trend in the future. So NASA obviously has an open data policy, but now it's transitioning to an open science policy, which means that any product funded by NASA, all of the code is going to be available as well as the data. And I really hope that this will allow us to move forward and not get confused as much. And hopefully that transparency will lead to increased uptake. Okay, so what have we learned from comparing biomass products? I'll give a couple of quick slides, and then Heather Kay, who's at the back there, she's going to be giving a presentation on this activity tomorrow. Okay, so this is very similar to a figure from Ralph's paper. This is comparing GEDI biomass estimates to the FAO FRA estimates. And so this is because we need some reference data if we're going to decide like what's working better where. Let's compare it to something. So this is often based on NFIs, the FRA reports, but sometimes it's based on other approaches for national reporting. So in general, GEDI is pretty close to these FRA numbers, a little bit off in Brazil, quite a bit off in China, and that might be because we don't have training data in China. I don't know, something to look into. But Neha Joshi-Hunka in my group has been looking at this comparison for the other biomass products as well. Again, all of the source code is available. And so looking at the CCI compared to FAO's FRA, China's looking okay, but the tropics, it looks like CCI is a little bit over there. So trying to figure out why. And we can do that analysis for many other products as well. Here's showing an animation going from the JPL distributions of biomass over 3 example countries to the GEDI, to the CCI. And so looking at these histograms is also really helpful for us. So for like, if one product's predicting over, is it like the high biomass is being predicted high? Is it the low biomass? It's a lot to unpack, and it's a lot for us to try to understand at a global scale as we dig in. One thing Nate has been working on is looking at whether the CCI and JPL maps fall within GEDI's 95 percentile confidence interval. So essentially, do the maps like statistically match or not? And it's a mixed bag. For a lot of this, no, they don't. Like there's serious discrepancies between these products, and we really have to do some more work to understand why. So using NFIs is extremely important here. So this is from Ralph's paper again, looking at the GEDI product versus the forest inventory analysis data, so the NFI in the US. And it helps us understand that there are some spatial patterns here. So like in general, we are underestimating a little bit through like kind of Western US, particularly in the sort of Sierras. We're overestimating at kind of the deciduous broadleaf forests out on the East Coast. So trying to understand where we're over and underestimating helps us refine and improve our products. Without that NFI data, we just don't have that information. And this is true for the tropics as well. So this is where our partner countries really come in and help us out. So this is an example for Ecuador. If we just look at comparing the totals at the national level, we don't really learn much. But if we start talking to the people doing and managing the NFI data, and looking at distributions from the different maps in different sub-national areas, biomes, we start learning a lot more. Okay, so this is still all very provisional. I wanted to highlight that there is a plot to map tool from ESA. This is led by Arnon Araza from Martin Harold's group, where if you have good reference data, like NFI data, you can start to do aggregated validation of different products. And this is an open science tool as well that runs on the map, but runs elsewhere. And in general, what we're seeing is that, unsurprisingly, typically remote sensing maps are underestimating high biomass and are closer to doing well at the low end, but with a slight overestimation at the very low end. That's kind of the trend across the board. For GEDI, we're not seeing as much of the overestimation at the low end in most places, but I heard yesterday that there was some. So we're still trying to like sort all this out, yeah? You can check out Arnon's paper in RSE, which is a really nice read, and he compared 4 different 2010, I believe, or 2010-ish biomass maps. Okay. So I know I'm talking a lot about intercomparison, validation, etc. Maybe that's not like as thrilling to a lot of you, but I think this is like super, super critically important, especially as we do have those new missions on the horizon. So as NISAR goes up, as biomass goes up, we're just going to be drowning in data, and combining these data almost for sure will do better than just using one data stream on its own. Yeah, like data fusion, I think is the way to go. But as we have more and more biomass products come out with different algorithms, we really are at risk of getting confused. So I think having these transparent kind of quasi-automatic tools for doing the intercomparison and validation will become even more important. All right, so if you're sitting out there being like, cool, tell me what biomass product I should use. Part of me is like, just use GEDI, but no. We don't know. We don't know. I think it'll be dependent on the application, but please do stay tuned and go to Heather's talk for more information. And here is, again, a messed up, some of the text has been kind of transferred weird, but you can check out the dashboard. As we do improve the products, we'll update them on this dashboard. Okay. So transitioning to what I think can improve these maps over time. So as we all know, maps are only as good as the data used to train them. Yeah, so like we're always trying to build up this database, but the database is imperfect. And just like for many of the past biomass maps, GEDI also has that dirty little secret of we use generalized allometries. Yeah. So as you all know, if you do anything in biomass, we are not actually weighing trees in the field. We can't coerce trees to step onto scales. We are using these allometric models that are usually based on a fairly small sample size of destructively harvested trees. And we are predicting biomass as some function of measurable attributes. There's John in a redwood in Sonoma County. Where is he? There he is. And so, like, can you actually predict the biomass of this massive tree based on the DBH and species alone? But that's what we do. That's what we do for all of these EO biomass maps, yeah? So I think that this is one of the main limitations. And as we start to see more and more uncertainty in the high biomass domain of our maps, I'm like, I'm not surprised, because we know these allometric models get worse as we go to bigger and bigger trees. So we just don't have that much that's been destructively harvested, kind of thankfully, for huge trees. But also there's a lot more structural variability as trees age. So this is where I think the TLS community, many of you, can play an increasingly important role. So here's a figure from Matt Disney's 2020 paper from some work we did in Sonoma County. So you can essentially do allometrically independent biomass estimation if you have TLS. Yeah, you do the whole woody volume, multiply it by a wood density, and you can scrap allometries. That's at this point unrealistic to get like TLS everywhere. Maybe in the future we'll be like, yeah, we don't do DBH anymore. We just put the TLS. But at this point, I think it's a bit unrealistic. I think more realistic would be to refit the allometries using TLS data to really improve them, especially for those big trees. And I know Matt's group and others are really invested in this. So that's, I think, an area of great interest. Here are a few slides from Kim Calder's, just showing off, you know, the difference between destructive harvesting and QSMs, and his work has demonstrated that you can indeed do this. Yeah, you can do better with TLS than you can with traditional allometries. Still not perfect, but this is from his paper in 2015 that showed that especially for the big trees, you do a lot better than with the traditional allometries. So I think this is one of the reasons we struggle in high biomass forests. Okay. Another comment on the GEDI products and how they're going to improve is if we can keep GEDI on orbit longer, the gridded products in particular will look a lot better. So we've heard from many people in the community that they're like, I would love to use GEDI. You've literally never gone over my area of interest. Like, oh, awkward. And then the other people are like, yeah, it's like a time series. It's amazing. You go over every week. And we're like, so this was not how it was designed. GEDI was, the ISS was supposed to have a certain altitude, and it essentially just went unexpectedly to a higher altitude. I think this was to like save fuel. And when that decision was made, the science missions on the ISS weren't consulted. And it made a big difference to GEDI because it stuck the ISS in kind of this orbital resonance pattern where it kept going over the same places again and again and again and missing like the next forest over. So we have like a wealth of data in some places, and unfortunately we have these big spatial gaps in other places. And so the solution is pull the ISS back down to its original altitude, which it's on its way there. It's not all the way, but it is actually being pulled back down, and then keep GEDI on orbit for longer, which I wish I could like say, and we are, but probably we're not. So we'll see what happens there. But we are hoping that at least for the next few months, until at least February of next year, when GEDI might end up being retired, which will be very sad, but at least we will hopefully start filling those data gaps in the next few months as that altitude continues to decrease. Okay, so now for the last maybe 10 minutes or so of the presentation, I'm going to focus on some of the kind of exciting new things that have been coming out of GEDI. So not just biomass, but like what can we do with GEDI data? So here's a slide from John's work. And this is in a place that does have that richness of GEDI data. This is at Witham Woods in the UK, a forest geosite, where if you're at like those kind of high latitudes where the ISS starts turning and going back south, you do get more data. So like Vancouver Island, it's like super, super packed with data, and so are parts of the UK. And so what John has showed is phenology from GEDI, which is pretty cool, yeah? So here we have May of 2019 through spring of 2021, summer of 2021, and you see canopy cover going up in the growing season, then back down. We didn't think that you could use GEDI for a time series, but you can in some places, which is really, really cool. And I think will kind of open some doors for some exciting new unexpected GEDI research. Okay, so there's Witham Woods in the summer, leaf on, and winter, leaf off. So you can see there is a big structural variation there, and that is being captured by GEDI, which is super cool. Some other really exciting work, this is from Lei Ma, who's going to be giving a presentation in the GEDI session after this. So this is using the ecosystem demography model, the ED model, initialized with GEDI to map biomass. And you're like, okay, but GEDI already does that. But you can use that model to forecast biomass flux into the future, which is super exciting, right? So using ecosystem modeling with GEDI enables us to ask all sorts of carbon cycle questions. So go to Lei's talk for more on this, but super cool work. And then I'm going to end my presentation with a few slides to talk about my passion project, which is now looking at protected area stuff. So like my comfort zone is more like algorithm development, playing with LiDAR data, but I've become increasingly interested in forest conservation. Just obviously it's very important for the global carbon cycle and very timely. And GEDI does enable us to do like global scale structural research, looking at questions like, has the creation of global protected areas actually led to more biomass? Are these being effective for carbon? Whether or not they were established for carbon, usually not, but has this led to more biomass? So this is work out of my group. I wanted to also highlight Amber Liang, Veronica Leitold, and Sruthi Pavarti Murthy here. So it's not by design, but randomly like all women leading this work, and we've been having a lot of fun poring over the GEDI data record and analyzing it. So the take-home message from this paper, which is still in review, hopefully that will come out soon, is that for all of the GEDI domain protected areas, they store a whopping 125 petagrams of biomass, which is 26% of all of the biomass in the GEDI domain. So like, that's a huge amount of biomass that's falling into these protected areas. But the main take-home message is that we've attributed about 20 petagrams to the existence of these PAs. So if you didn't have the protected status, we think that about 20 petagrams of biomass would have been lost. And this is roughly equivalent to 1 year of annual global fossil fuel emissions. So this is like a lot of carbon. Is it going to, solve the climate crisis? Absolutely not. But it's very important, and it's painting the picture of the carbon importance of these areas. So to do this work, you might be like, how the heck did you come up with that? So obviously GEDI is not this time series. Yeah, we don't have GEDI data year after year after year. We have essentially a stock of a few years around 2020. So what we did was we said, okay, back in the year 2000, let's look at protected areas and let's match every single protected area to other areas that should be the exact same, except they don't have protected status. So like the same distance to roads, the same climate, the same soils, the same canopy cover, like in the year 2000, they were the same. And then let's see how much biomass is in the protected areas versus their matches in the year 2020 from GEDI. So it's sort of like space for time. And what we found is that not only are they very effective, but this changes a lot spatially. So the vast majority of the signal is coming from moist tropical forests in South America, specifically Brazil. So Brazil hosts a lot of biomass, the most in the world, right? About half of that actually is protected, falling in protected areas. But if it's not in a protected area, those forests are disappearing. And that's what we're seeing in this signal. This is avoided emissions from deforestation. In general, across the board, these tropical moist forests do dominate the signal in most places, so including Asia. In Africa, interestingly, we see dryland forests, woodlands, and shrublands. That's where we're seeing more of the carbon signal, which is interesting, and I don't have time to dive into that today. But what we're, so the like attributed extra biomass due to the existence of protected areas, obviously we don't say, we're not thinking, hey, if that wasn't protected, it would be clear cut. We're just seeing this difference between those protected areas in 2020 and their matches in 2020. So that is like this dark green at the top of these bars. These are the top 20 countries ranked in terms of their total national aggregated effectiveness for biomass preservation. So Brazil comes in #1 place here, followed by the United States, and then Indonesia, DRC, etc. And then on the right here, this is actually a typo. This should be the US, not Australia. Sorry, Australia. You're like 1, 2, 3, 4, 5, 6th. Because apparently I got a bias for Australia. Yeah, and then in terms of like what percentage of national biomass falls within protected areas, we also ranked that just out of interest, and we found that Cambodia comes out on top. So in Cambodia, more than 60% of the biomass falls in protected areas. Maybe the rest has been lost, I don't know. But so this highlights that yes, this dark green that's attributed, we think this would have been lost without protected areas. It's important, but for most countries, it's a very small part of the pie. So there's a lot of other biomass both in and outside of protected areas. Maybe that should also be protected. Can this type of information actually inform conservation decisions? I don't know. Okay, so this is my last results slide before I show a little video. And this is a very confusing little blob, but this is my take home from this. Okay, we'll walk through it a little bit. Is that GEDI can see structural discrepancies that the optical signals can't see. So we looked at our GEDI structural signals, so the difference between protected areas and our matches in terms of biomass. And then we compared it to the forest loss products from Matt Hansen's group. So we're like, okay, where we're seeing more biomass in the protected areas, are you seeing more forest loss outside of the protected areas with the optical signal? And for 30% of the data, that's what we see. So like Landsat and GEDI are like, we agree here, and we agree down here, where GEDI says, hey, in these protected areas, there's less biomass. What's going on? And the optical signal's like, yeah, there's more disturbance inside the protected areas than outside of them. So some protected areas are not actually working well for carbon. So it's like GEDI matches here with Landsat, GEDI matches here with Landsat. But I think it's really interesting to look at these other quadrats. So up here, GEDI is saying there's more biomass in protected areas. And the Landsat signal's like, I don't see a difference. I don't really see a difference. If anything, I see less canopy cover loss outside of the protected areas. What I think that is protected areas leading to avoided degradation, and that degradation not being visible in the optical signal. I really want to compare this with some of the like Sentinel-1 based products to see if maybe we can see some of that disturbance in the radar that we're not seeing in the optical. And then conversely, down here, GEDI's seeing less biomass in the protected areas, and Landsat's like, there's either no difference, I don't know. So this is where Landsat's not seeing forest loss in the protected areas, but GEDI's seeing less biomass there. Is this some sort of degradation within the protected areas that Landsat can't see? So the take-home message here is that GEDI really does, as we would expect, it's able to see structural differences that we can't see, at least in the optical signal. I think that in the C-band SAR signal, we probably won't be able to see either because it's a different data set, yeah? So I think that this is just an example of the power of GEDI to start asking different structural questions than we've been able to ask with other data sets at these global scales. Okay, and that made me think of the difference between the GEDI launch and the Landsat-9 launch. This is where I'll end my talk. So here we have, do I just click play and it'll go? Yeah. So this is the GEDI launch. I apologize, I'm literally taking it with my phone.
7, 6, 5, 4, 3, 2, 1. Yes! Oh yeah, go!
Very exciting. Like launch so slowly.
Whoa. Done. You can make it!
There it went. Okay, then you can start to hear it a little bit. And then the video sort of cuts off and we all just started dancing around like maniacs. So that was the GEDI launch. How amazing, and what amazing visibility. Great data. Here's the Landsat-9 launch, and I love Landsat-9. This is no shade on it, but this was very funny because a lot of us got up super early in the morning to go to this amazing launch.
I don't know what's that, right?
We're at the end of some random runway.
Go Landsat-9.
Or
6, 5, 4, 3, 2, 1.
Didn't even know where we were looking. We're like, yeah, that was it. All right, so, you know, we can see stuff with GEDI. So I'll just make a couple of sort of closing take-home remarks and then I'll finish there. But so as we said, GEDI and ICESat-2, they have enabled these new biomass products. Yeah, the estimates in general are larger than the old EO estimates. We want to dig into why. We're working on that. It's TBD whether these products are actually going to be used for policy, and we really have to work with the people making those decisions to make sure that that happens. Because of course, our community really does believe doing this with EO is better than like stratify and multiply, right? Oops, no. Okay, secondly, we are going to have, and we welcome this, a lot of new awesome approaches to mapping biomass, yeah? But more products equals more confusion. So open science, I think, is the way to go. Talk to each other, try and get involved in some of these intercomparison activities. And my take home really is that in terms of GEDI, we are just scratching the surface of science. So we've all been experiencing a pandemic. We haven't had a lot of time to just take a step back and do creative new science. My protected area study is just like one thing that I wanted to highlight, but I'm sure that there's a lot of really cool science that will come out of this community. And I really do encourage you to take a step back, think about what GEDI can do, and do something really new and creative with it. Future missions are going up in the next few years. This is only going to increase the amount of amazing data available. I think when we were talking about like this golden age for LiDAR at the last Forasat, I think this is like an increasingly golden age for both LiDAR and radar and optical and data fusion. So have fun playing with the data, and thank you so much for your attention.